Hello friends, in the last few sessions, we have covered the basics of link layer and discussed in brief some of the services provided by link layer and error detection and correction techniques adopted by link layer. We have also discussed the multiple access protocol, typically the channel partitioning protocols. Now, in this session, we will discuss yet another category of multiple access protocol, that is random access protocol. The second broad class of multiple access protocol is the random access protocol. In random access protocol, each and every transmitting node always transmit at the full rate of channel. That is, each competing node involved in transmitting the data over the shared channel use the full bandwidth of the channel. That is, here in this case, the R bits per channel. As there is no synchronization among the nodes competing for a shared channel, there is a likelihood of collision of the data. And when there is a collision, each node involved in the collision repeatedly retransmits its frame or data or a packet until its frame or a packet or data is get through without any collision. But when a node experiences a collision, it does not necessarily retransmit the frame right away instantaneously. Instead, each node waits for a random duration of time, and hence the name random access protocol. That is, each node waits for a random delay before initiating the retransmission of the frame. Each node involved in the collision chooses the random delay independently. This is most important. Because the random delay is chosen independently, it is possible that one of the nodes will pick a delay that is sufficiently less than the delay of the other colliding nodes, and hence will be able to send the frame into the channel without any collision. There are dozens of random access protocol available. The most commonly used are the ALOA protocol and the carrier sends multiple access protocols with various versions. Slotted ALOA is one of the simplest random access protocol. Here in our discussion based on slotted ALOA, we will assume that all frames consist of exactly the same number of bits, that is L bits. Time is divided into slots of a size L by R, where R is the channel rate. That is, a slot equals to the time to transmit one frame. Node starts to transmit frame only at the beginning of slots. The nodes are synchronized so that each node knows when the slot begins. If two or more frames collides in a slot, then all the nodes detect the collision event before the slot ends. Let P be a probability that in which is a number between 0 and 1. The operation of slotted ALOA in each node is very simple. When the node has a fresh frame to send, it waits until the beginning of next slot and transmit the entire frame in that slot. If there is not any collision, the node has successfully transmitted its frame, and thus need not consider retransmitting the same frame. That is, a node can prepare a new frame for transmission if it has one to send. But if there is a collision, the node detects the collision before the end of the current slot. The node retransmits its frame in each subsequent slot with the probability P until the frame is transmitted without any collision. By retransmitting with the probability P, we means that node effectively tosses a biased coin wherein event head corresponds to retransmit, which occurs with the probability P, and the event tail corresponds to skip the slot and toss the coin once again in the next slot, which occurs with the probability of 1 minus P. In this slotted ALOA, all nodes involved in the collision toss their coins independently. This is how slotted ALOA operates. The slotted ALOA random access protocol would appear to have many advantages. Unlike the earlier channel partitioning multiple access protocols, slotted ALOA allows a node to transmit continuously at full rate, that is R bits per second, when the node is the only node which is active node. That is, a node is said to be active if it has frame to send. Slotted ALOI is also highly decentralized because each node detects collision and independently decides when to retransmit it. There is no synchronization as such among the different nodes. Slotted ALOI is also an extremely simple protocol. Slotted ALOI works well when there is only one active node. But how efficient it is when there are multiple active nodes? There are two possible efficiencies concerned here. First, as shown in the figure, when there are multiple active nodes, a certain fraction of the slot will have collision and will therefore be resulted in waste. The second concern is that another fraction of slot will be empty because all active nodes refrain from transmitting as a result of probabilistic transmission policy. The only unvested slot will be those in which exactly one node transmits. That is, a slot in which exactly one node transmits is said to be a successful slot. Here, the first category here is node 1, node 2, and node 3. All these three nodes are transmitting simultaneously in the same slot. Hence, this will result in collision and that particular entire slot is wasted. The second category is none of the node is data to send in this particular slot. This particular slot is remain idle. This may be result because of all the active nodes refrain from transmitting, which is as a result of probabilistic transmission policy. The time to retransmit is selected independently and the delay time is also random, which may result in certain slots may remain idle even though all the nodes computing have data to send. The only unvested data, that is the properly utilized data, is wherein in any particular slot, for example this S slot, only one node is having data to send. So we can term this slot S as a successful slot. S indicates a successful slot, C indicates the slots with collision, and E indicates the empty slot because these slots were not used by either of the nodes. These are the certain drawbacks of slotted ALOA. The efficiency of slotted multiple access protocol is defined as to be the long run fraction of a successful slot in the case when there are large number of active nodes and each one have large number of frames to send. Note that no form of access control were used and each node were to immediately retransmit after each collision. Efficiency is bound to be zero. And it is evident that the slotted ALOA clearly increases efficiency beyond zero. We'll now try to briefly outline the derivation of maximum efficiency in case of slotted ALOA. For better understanding and to keep the derivation simple, we will modify the protocol a bit and assumes that each node attempts to transmit a frame in each slot with the probability of P. That is, we assume that each node always has a frame to send and that the node transmit with the probability of P for a fresh frame as well as for a frame that has already been suffered collision, that we term it as a retransmission of a collided frame. Suppose there are n nodes, those who are competing for a common shared channel. Then the probability that given slot is successful slot is the probability that one of the node transmit and that the other remaining n minus 1 node do not transmit. As we have seen in the earlier figure, we can say the slot is successful when only one node is transmitting. Indirectly, it means that all remaining n minus 1 nodes are not transmitting. Hence, the probability that given node transmitting is P and the probability that remaining nodes do not transmit is 1 in minus P into n minus 1 or raised to n minus 1. Hence, the probability that a given node has success in a slot is given by the product of both P into 1 minus P raised to n minus 1. And since there are n nodes, probability of any given node as a success is given by n into P into 1 minus P raised to n minus 1. This is the probability for a single node. But as we are having n nodes, probability that any node has success in a slot is given by n into P into 1 minus P raised to n minus 1. If you wish to calculate the maximum efficiency, that is given by, we need to find the probability P star that maximizes this particular value, n into P into 1 minus P raised to n minus 1. Thus, when there are n active nodes, the efficiency of slotted ALOA is given by n into P into 1 minus P raised to n minus 1. And the effective transmission rate of a channel is not the entire transmission capacity, that is R, but it is only 0.37 times R. In conclusion, we can say that at the best, channel used for useful transmission is only 37% of the time. Means only 37% of the time of the entire duration of time may be used for successful transmission. The slotted allow protocol requires that all nodes synchronize their transmission to start at the beginning of a slot. The first allow protocol was actually an unslotted, fully decentralized protocol. In pure allow, that is unslotted allow protocol, when a frame first arrives, that is network layer datagram is passed down from network layer at the sending node. The node immediately transmits the frame in its entirety into the broadcast channel. If a transmitted frame experiences a collision with one or more other transmissions, the node will then immediately, that is after completely transmitting its collided frame, retransmit the frame with probability P. Otherwise, the node waits for frame transmission time. After this wait, it then retransmits the frame with probability P, or waits, that is remaining idle, for another frame time with probability of 1 minus P. Here there may be chances that as it is a pure, that is unslotted ALOA, overlapping of the frames from different users may be possible, as it is completely unsynchronized. Transmission of packet by individual node may start anytime, not compulsorily at the beginning of each slot. Hence, partial overlapping of the nodes or packets or frame from different users is possible in case of pure ALOA. To determine the maximum efficiency of pure ALOA, we will focus on individual node. At any given time, the probability that node is transmitting a frame is P. Suppose this frame begins transmission at time T, 0. As shown here, in order for this frame to be successful, suppose this frame has started transmission and began transmission at time t0, and suppose in order for this frame to be successful, no other frame should be allowed to begin the transmission either in one of the slots, that is from t0 minus 1 to t0, no other frame should be allowed to begin the transmission. Again, no other frame should be allowed to begin the transmission in between t0 to t0 plus 1. Because such a transmission would result in overlapping with either the beginning of the transmission of node I frame or the latter part of the frame of the node I. The probability that all other nodes do not begin transmission in the interval t0 minus 1 to t0 is given by 1 into p 1 minus p raised to n minus 1. Probability of success by given node is given by probability of node transmits into the probability of no other nodes transmits in time slot t0 minus 1 to t0 into the probability that no other nodes transmits or begin transmits in duration t0 to t0 plus 1, and the probability that all other nodes do not begin transmission in the interval T0 minus 1 to T0 is given by 1 minus P raised to N minus 1. Similarly, no other nodes can begin transmission while node I is transmitting. As such, a transmission would overlap the latter part of node I transmission. The probability that all other nodes do not begin transmission in this interval T0 to T0 plus 1 is given by again 1 minus P raised to N minus 1. Thus, the probability that a given node has successful transmission is given by P into 1 minus P raised to 2 times N minus 1. And as N tends to infinity, this comes out to be 0.18, exactly half of that of the slotted ALOA. This then is the price to be paid for a successfully decentralized asynchronous pure ALOA's protocol. The efficiency is exactly half that of the slotted ALOA. Here in this session, we have covered the details about max random access protocol like slotted ALOA and ALOA, that is pure ALOA. In the next part, we will cover the CSMA and CSMA CD in detail. Thank you for being with me. Thank you.